So hi everyone, welcome to our talk, Bugs on the Windshield, Fuzzing the Windows Kernel. We know it's been a very long day with many interesting talks, and we hope you enjoy, we thank you for sticking around, and we hope you enjoy watching this presentation as much as we had making it. So just a little bit about us. My name is Yoav Alon. I'm the CTO at Orca Security. I've been a security researcher for 10 years. It's a bit redundant. And recently, I've been added to MSRC, Most Valuable Security Research List for 2019.
My name is Netanel Ben Simon. I'm a security researcher at Checkpoint Research, and I'm also in the same list as you have.
We had a pretty successful fuzzing campaign, fuzzing binary format parsers in user space. We found multiple vulnerabilities in formats such as JPEG, PDF, WMF, and so on, and targeting mostly Adobe Reader and Microsoft Edge. If you want to check out if you want to read more about this research, you should check out Checkpoint Research blog for more details. But at this point, we were wrapping out the previous research, and we felt that we wanted a bigger challenge. And fuzzing Windows kernel seemed hard enough. And as a net bonus, we can use our user space vulnerabilities, chain them together with our newly found kernel vulnerabilities, and get a full chain, which is pretty cool. So since this is a fuzzing presentation, I'm going to do a really quick recap of what is fuzzing. Fuzzing is a method for automatic software testing. It's the most cost-effective way we know for finding real bugs in real software. The inputs for the process are the target CPU, what you want to fuzz, and CPU time. And the outputs are hopefully bugs. An example of a very basic fuzzer is wrandom. It just pipes random bytes into the std_in, and this was a killer fuzzer back in the 90s. Fuzzing is also a very active area of research, and as you can see from the graph, the number of publications per year grows very rapidly. In this talk, we're interested in modern fuzzers. So modern fuzzers consist of three major things. One is a test case generator and mutator, which is responsible for automatically generating inputs. A bug oracle, which is something that detects buggy conditions. That usually means segfault, but it can be any other thing, like asserts, memory leaks, and so on. And finally, we need some sort of a feedback mechanism, which in modern fuzzers is usually coverage, but it can be any other metric that you can target, like CPU cycles, memory, and so on. Examples of modern fuzzers are AFL, libfuzzer, hongfuzz, and a few others. And if we look back at the example of our previous fuzzer, we can see that wrandom has a test case generator, random. It's not a very good one, but it exists. It has a bug oracle. It can detect segmentation faults, but it doesn't have any feedback mechanism, so definitely not a modern fuzzer. So let's see the process of coverage-guided fuzzing and how it works internally. So we start with an initial corpus, which is a fancy word for a bunch of inputs, usually files. We take the inputs and import them into the fuzzer queue. We either generate new input or select one from the queue and mutate it randomly, and then we feed it to our coverage instrumented program. Then, if the program crashed, that's great. We have a bug. We can triage it and save it. Triaging means looking for duplicates. Otherwise, we will check if new coverage was detected. When we say new coverage, we usually mean new if statements were arrived. If it was so, we'll try to minimize it and save it. Otherwise, we'll discard it and keep on going. This is basically how every coverage-guided fuzzers work, AFL, libfuzz, hongfuzz, and all others. So back to our research, we said to ourselves, well, we have an experience with AFL. Can we use AFL to attack OS kernels? And the answer is yes. There's KAFL, which is AFL with a K, and K stands for kernel. So KFL is a research fuzzer from the Bochum University that leverages AFL-style fuzzing for attacking OS kernels. KFL supports Windows, Linux, and Mac OS, and it was used to find real bugs in real software, which is kind of what we're after. KFL has a pretty interesting architecture, and we're going to review it very quickly. The main fuzzer runs on the host, and when it starts, it will spawn multiple virtual machines running the target OS. in the agent, there will be a preloaded, in the VM, there will be a preloaded agent that will cooperate with the fuzzer to drive the fuzzing process. The fuzzing loop looks something like this. First, the agent will request an input from the fuzzer. The input will be transferred through shared memory. Then the agent will send a request to the hypervisor to tell him to start recording coverage. We'll talk about exactly how in a moment. Then the agent will pass the input to whatever we want to attack. In our example, it's test sys. And finally, it will tell the hypervisor to stop tracing coverage and pass the coverage back to the fuzzer. KFL's coverage implementation uses Intel processor trace. For those of you less familiar, the Intel processor trace, which is also known as Intel PT, is a low overhead hardware execution tracing feature in the Intel CPU. It uses the hardware to write trace information into compressed memory, and KFL uses a fast decoder to decode those traces into full traces. Finally, how does AFL detect crashes? Well, when the agent is first loaded, the agent will send the addresses of bugcheck and bugcheckx to the hypervisor. The hypervisor will patch the addresses of bugcheck and bugcheckx with a special shellcode that each uses a hypercall. When the system crashes, the kernel will call bugcheck and bugcheckx, which in turn will call KVM, which in turn notify the fuzzer that we crashed. And this is a screenshot for KFL's dashboard. If you blink fast enough, it kind of looks like AFL. So what should we attack with AFL or KFL? So from our experience, good targets for AFL or KFL have a few characteristics. The first one is they're fast. They're able to execute hundreds of iterations per second. And the second thing is they're parsers, specifically for binary formats. Those are the best targets. So we can ask ourselves, which fast binary format parsers live inside the Windows kernel? And the answer, there are quite a few. There are the file system and file system-like formats like registry, and NTFS, CLFS, FAT, and so on. There's the device drivers that parse binary information. There's the crypto API that uses some of it. There's the PE format that actually Dave talked about before, and a few others. We looked at this map and we said to ourselves, let's take a step back. Let's look at a typical kernel vulnerability. In this case, CV 2018-0744. You don't have to really read the code. You just have to look at the structure of the code. And you can really see that it has a few properties. The first one, there are many system calls here. There's not just one. And they all receive highly structured data, like structs, magic numbers, function pointers, strings, flags, and so on. And notice that there are dependencies between the calls, meaning that the output of one call is the input for the next call, which means that, and this is pretty common for a kernel vulnerability, where we don't actually parse anything binary, but there's a sequence of calls that reaches a state where a vulnerability is triggered. And these are the kind of vulnerabilities we want our fuzzer to find. So going a step back, what KFL provides us is a binary blob, and what we want is a sequence of semantically meaningful syscalls, preferably in a C file. So at that point, and if we look back at the available attack surface when looking at KFL and compare it with a syscall fuzzer, we can see that the map now drastically changes. And this provides us, as an attacker, much more room to work with. So we decided to dump KFL and move to a syscall fuzzer. And we did what every good researcher does. We used Google to find the syscall fuzzer. And so we found syscaller, and I'll call Netanel to the stage to tell you all about it.
Thank you. Syscaller is coverage-guided structure-aware kernel fuzzer. Try saying this 5 times in a row. It's also known as a smart syscall fuzzer. It supports multiple operating systems such as Linux, FreeBSD, Fuchsia, Android, and others. It supports running on multiple machine types such as QEMU guest, Google Cloud Engine instances, mobile phones, and so on. It also supports multiple architectures like x86-64, 64-bit ARMs, and others. Syscaller is also known in some circles as the hardest working researcher in the Linux kernel community. To date, it has found around 3,700 bugs in the Linux kernel. One example is CV 2019-2215, a use-after-frame binder which was found being exploited in the wild. As you can see in the screenshot below from Sysbot, Syscaller's online dashboard, it was found 2 years prior by Syscaller. If you recall from a few slides ago, these are the 3 foundations of modern fuzzers. Let's see how Syscaller answered these criteria, starting with test case generator mutator. Syscaller generates programs, which are a sequence of syscalls. Let's look at an example of a program generated by Syscaller. This program opens a file called file0 and assigns its result to R0. This weird pointer assignment syntax are instructions to write the string file0 to memory and pass its pointer to the open syscall. This syntax is not only used for strings, but also for describing memory layouts of structs, buffers, unions, and so on. Next, the program reads 57 bytes from the file to memory. And finally, it closes the file. But how does Syscaller generate programs? Well, it uses syscall descriptions. Syscall descriptions are how you as a researcher define to Syscaller how to call syscalls. It's basically the recipes used by Syscaller to bake programs. Let's look at a simple syscall description. For example, the syscall exit, which has only one parameter, the error code, which is an int. Notice that Syscaller has a Go-like syntax, where the argument type comes after the argument name. A more complicated example is the open syscall, the closed syscall, sorry. This syscall receives a file descriptor, which is technically an int. However, we know that file descriptors are a kernel resource, meaning that random number would just be rejected by the kernel. Sorry. This syscall receives a file descriptor, as I said earlier, meaning that random numbers will just be rejected by the kernel. That's why Syscaller has the concept of a resource, which is a type that it cannot generate by itself, but it has to use other syscalls to obtain it. An example of syscall that generates a file descriptor is the open syscall. Syscaller also supports flags, structs, unions, and more. In the case of open, it knows that open mode is a flag, which means it can use one or more flags together. Last example is the read syscall. The syscall receives a buffer as an input, which it will write up to length bytes to it. Notice that buffer and length have a semantic relationship, meaning that if the length is bigger than the buffer, the syscall will probably fail. Syscall descriptions are written to text file. Sysgen, which is another Syscaller tool, will take all the syscall descriptions and automatically generate a Go code that will be compiled into sysfuzzer. Sysfuzzer will then start generating programs by randomly selecting syscalls and making sure to satisfy all their dependencies. Syscaller are also able to mutate existing programs. Let's look at a few mutation strategies. Insert call, well, inserts a call, making sure to satisfy all the dependencies to call successfully the syscall. Mutate arg will mutate an argument according to its type. Splice will take 2 random programs and join them. Squash any will perform AFL style mutation on complex pointers, such as structs, buffers, unions, and so on. So clearly, Syscaller has a sophisticated test case generator mutator. Moving on to feedback mechanism. Now that we know how Syscaller generates programs, let's look at the bigger picture. The main binary for Syscaller is sysmanager. When it starts, it will do the following. It will load the corpus of programs, and then it will start the target machines. It will copy the fuzzer and executor binaries to the machine using an SSH. Then it will execute the fuzzer. At this point, sysfuzzer will establish connection with sysmanager. and start communicating by RPC. Then sysfuzzer will fetch the corpus from the manager and start generating programs. For each program, it will send it back to the manager in case of a crash. Then it will start the executor. Then it will send it to the executor, which will execute the sys calls and collect coverage from the kernel. Linux kernel coverage is done using kcov, which is a compile time tracing feature. Finally, sys executor will report back the coverage to sysfuzzer, which will notify the manager in case of a new coverage. Feedback mechanism, check. Finally, bug oracle. In case of a crash, Linux kernel will panic and print crash information to the output console. Sysmanager will then detect the output message and will report on a crash. Syscaller is usually used with ksan, kmsan, ktsan, and other sanitizers which greatly improve the syscaller ability to detect crashes. Bug oracle, check. Syscaller aims to be unsupervised, meaning it will try to automate the entire fuzzing process. In an ideal world, fuzzers are just plug and play. But like Charlie Miller used to say, working with fuzzers is like babysitting an army of monkeys. In the case of crashes, sysmanager will spawn multiple reproducer machines. In the process of reproduction, syscaller will dissect the crashing programs from its log and will try to minimize them. When the process is finished, it will either reproduce a sys program like we've seen earlier, or a C code, which will reproduce the crash. So to recap, syscaller is awesome. But syscaller is for Linux. Well, actually, before this presentation, we talked to Dmitry Vyukov, which is the founder of syscaller, and he corrected us. Syscaller is not only for Linux, but supports other operating systems as well. So when we say syscaller is for Linux, we actually mean syscaller is also for Linux. So let's run Linux on Windows. What is WSL? WSL is a compatibility layer for running Linux binaries natively on Windows. It translates between Linux syscall to Windows API. It allows to interrupt Linux Windows and Windows binaries. For example, you can run the task list from bash and count the number of lines. It requires less resources when running a full virtual machine. And finally, it was designed to run bash and call Linux commands for developers. Let's see how does it work. Starting from Windows 10, there is a new type of a lightweight process called Pico process. When the Pico process issues a syscall, it will pass the anti-kernel to a dedicated driver called Pico provider. In the case of WSL, the Pico processes are Linux binaries, and the Pico provider, LXS and LXCore, will translate the Linux syscalls to Windows system calls. At this point, we decided to fuzz WSL because fuzzing WSL is very similar to fuzzing Linux kernel. We can reuse most of the existing grammar and the executor. It is relatively new, has two drivers which are around 1 megabyte of code with little CVEs. And finally, we wanted to find bugs for full chain, but we also wanted to get some experience with syscaller on Windows. So it looked like a good first step for us. Looking at syscaller architecture, we need to change a few things to fuzz WSL. We need an SSH server, which is easy. We have a Linux distro for that. We need to find a way to collect coverage. And finally, we need a mechanism to detect crashes and deduplicate them. So how to get tracing coverage? Windows is closed source compiled binary, meaning we can't use a compile time tracing feature like kcov. So we thought a few alternatives. The first one was using an emulator like Box or QEMU and adding coverage instrumentation. The second option was using static binary instrumentation for coverage like in PAFL. Another option was using a hypervisor with sampling coverage like in ApplePie. But at the end, we settled on using Intel PT for coverage. like in KFL. What we did was to add patches to KVM to support coverage with Intel PT. We used large parts of KFL KVM patches for that. In addition, we exposed the K-code-like interface through hypercalls. So now, when the executor tries to start, store, or collect coverage, it will communicate with the KVM instead of the kernel. We also added support for exporting coverage in DynamoRio format, also known as DRCOV format. We used IDA and the awesome Lighthouse plugin to visualize the coverage. Here's an example of how Lighthouse visualized the coverage by adding colors to executed basic blocks. As for bug oracle, we used the same technique as in KFL. In case you already forgotten, we patch bugcheck and bugcheckx with the shellcode that issues a hypercall on a crash. We added regex to identify crash from QEMU output, and finally, we enabled driver verifier with special pulls for LXCore and LXSS to catch pull corruptions. A common issue with fuzzers is that they encounter the same bug many times. When the fuzzer finds a new crash, we want our fuzzer to be able to determine whether it's actually a unique crash or is it a duplicate. In order to decide this, syscaller has to get a unique output for each crash. In the case of Windows, we settled on a call stack. The symbolizer architecture is really awkward, and you should read the full blog post for all the details. Suffice to say, we had another Windows machine running alongside our fuzzer and reading memory from the guest OS and retrieve a call stack. This architecture was heavily inspired by Boxpawn for Windows. So after a lot of agony, we got from these random numbers to this beautiful call stack. So a quick recap. SSH server, check. Coverage, check. Crash deduplication and detection, check. So we started fuzzing WSL. And then it rained bugs. Well, not really. A short time after we started the fuzzer, we noticed a crash with critical structure corruption, and we were like, what the fuzz? So a quick Googling showed that it's actually PatchGuard. So why did PatchGuard come to our life? So let's return to how we detect crashes. Remember that we, in order to detect crashes, we patched Antos kernel. So good news, everyone. PatchGuard is working. What we first tried is to enable kernel debugging, but that caused random hangs in the guest. So what eventually we did was to write a small driver called Panic Reporter, which will register with Antos bugcheck callback, with K register bugcheck callback. So now when the kernel crashes, Antos will call the Panic Reporter, which will issue a hypercall notifying on a crash. Another issue we encountered is coverage stability. Syscaller uses multiple threads to find data races, but our coverage implementation had only one buffer per process. In practice, the same program would result in different coverage each run. Coverage instability hurts the fuzzer's ability to define the new and interesting paths and essentially bugs. What we did, TLDR, we added guest thread tracking to KVM and allocated buffer for each thread. If you want all the details again, you should check the blog. We had a few more minor issues, like autoloaded program that would starve our fuzzers, Windows Update restarted our fuzzers randomly, causing syscaller to think it's a hang. Windows Defender randomly decided that our fuzzer is a virus, and in general, take time and make sure you adjust it for best performance. So after 2 weeks of fuzzing, we got a working prototype for syscaller on Windows. 4 denial of service bugs, 2 that fit in a tweet, 2 deadlocks that are still not resolved, but 0 security vulnerabilities were found. We were a bit disappointed, but we decided to move to a real privilege escalation target. So now Yoav will come and talk to you about our next target.
So we looked back at the attack surface of the Windows kernel, and we decided to set our sights on Win32k. So first thing first, what is Win32k? It's the kernel side of the Windows subsystem, which is the GUI infrastructure for the entire operating system. It includes the kernel side of the window manager, also known as user, and the kernel side of the graphics device interface, also known as GDI. So why Win32k? Well, it's a very popular target for local privilege escalation, and we want the local privilege escalation. The reason it's a very popular target for local privilege escalation, it's because it has a huge attack surface with more than 1,500 syscalls. And although it has been fuzzed before, some would say to the death, we couldn't find any previous work of coverage-guided grammar fuzzing for that target, so we decided to go for it. Looking back at the architecture, we need to make additional changes. We need to change the fuzzer, the executor, a minor tweak to coverage. Our first attempt was just to rename everything to .exe and hope for the best. But since that didn't do the trick, we just had to do a real work. So for the executor changes, we needed to support up to 12 parameters per syscall because you know Windows. The second thing we had to do was to port some OS-related things like around thread management, shared memory, and pipes, not really interesting. And we had to expose Windows syscalls to syscaller. And we decided that we want to compile everything on Linux. Compiling on Linux was a bit of a drag because we needed Windows we needed MinGW to call all the Windows syscall. What we did is we took DLLs from Windows to Linux. We used a tool named GenDef to create def files. We used another MinGW tool to create import libs, and we used that to link everything to our executor. So finally, we can call Windows syscalls. The fuzzer also had a few changes around memory management, shared handles, and shared memory and pipes, but and of course we had to add Win32k grammar. We'll talk about Win32k grammar in a few slides. And for coverage, Win32k is not one thing, but three things. It's Win32k, Win32k base, and Win32k full. So, and our coverage implementation only supported one module. So what we did is we opted out to another coverage decoder from WinAFL, which is much faster and helped us. And we can see now coverage traces from Win32k, which is pretty cool. So quick recap: fuzzer check, IPC check, executor check, coverage check. What did we forget? Sanity check. So we took our fuzzer for a spin, and we tried to reproduce to CVE 2018-0744, which we showed before. But the fuzzer wasn't able to reproduce the bug. We were a bit surprised, so we investigated it a bit, and we discovered that our fuzzer was running under session 0, not under normal session user 1. The fix was pretty simple. We moved the SSH server from being a service to being a startup program. But the main conclusion from this is reproduce all bugs and test your fuzzers, because otherwise you're probably wasting CPU time. So after sanity check, we moved to stability check. We added about 15 APIs, and we let it run for the night. And we got a blue screen. Our first thought was patch guard, but we tested it without the fuzzer, and it was reproduced. So we thought maybe it's not patch guard. Our first bug was actually a use after free in open clipboard. But it only reproduced on some machines, and we were like, what the fuzz? Looking at the crashing code, we couldn't find clues to why it crashes, so we had to go to the binary. Looking at the binary, we can see that it crashes when it tries to fetch the process ID from the process information block. But the process information block is already freed. On machines that the crash reproduces, the if statement above the block evaluates the true. Well, what does it check for? Well, it checks if Win32k trace logging is turned on for a specific feature. What we found out through experimentation is that this feature is either turned on or off by boot. And it depends at install time, and it depends if you install the same machine a couple of times, it would either be on or off. And it felt like our fuzzer was part of an experiment So a feature experiment. So we don't always we don't always get A/B tested machine, but when we do, we found a vulnerability in one. So we went back to stability checking, and we reinstalled Windows, making sure that this feature is definitely turned off. And we got another bug. This time, it was a denial of service in register class EX, which is pretty weird, because register class EX is very basic. What we found out is the bug itself is not in register class EX, but in RTL allocate heap. Apparently, when you allocate specific sizes in specific points in time, you can actually cause the kernel to allocate from reserved pages and crash. So at this point, our motivation was really high because we added 15 syscalls and we found 2 bugs. And with 1,500 syscalls, we're going to find like 200 bugs, right? So yeah, at this point, we decided to commit to writing all the grammar. So writing grammar is a lot of work because there are a lot of syscalls and we're a bit lazy. So our first thought was automation. How can we automate this? There are a few problems. The first one is that the Windows headers don't contain enough semantic information to generate quality grammar. For example, every single duplicate type here means different things in different contexts. And the other thing is that Windows has a lot of undocumented APIs. Fortunately, Windows is technically open source because there's the Windows NT leaked sources, there's the Windows 2000 leaked sources, there's ReactOS, which is technically Windows 2003 leaked sources, there's the WRK, and a few other resources. So what we did was, for each syscall, we looked at the sources plus the documentation, and we tried to verify it as much as we can with static analysis and dynamic analysis. We became basically workers in the grammar mines. Most APIs are pretty simple, but others are really hard with terrible semantic relationship and complicated structures. Here's a few examples of system calls that we ported. It's just to see. So we let the fuzzer run for the day, and we got 3 new vulnerabilities within a day, and we let it run for the week, and it didn't find anything new. And we said, well, we want more. So at this point, we had to go a bit deeper. And I have to tell you something that not many people say. Fuzzers are not magic. What it means is that researchers have to help fuzzer to teach them by teaching them tricks and helping them reach hard-to-reach attack surfaces. Our process for doing that is we start from reading as much as we can about the attack surface, everything that we can get our hands off, prior work, old bugs, every research presentation we can see. We also try and reproduce all bugs. All bugs teach us a lot about the attack surface and about the fuzzer's ability to abilities and limitations. And finally, we take time to look at coverage maps. Coverage maps gives you a pretty clear map where your fuzzer is not targeting. And we take all of these insights and we try to inject them back into the fuzzing process. Let's see an example which is not so empirical. One thing that we learned through the research is there is such a thing called GDI shared handle table, which is an array of structured pointed by the PEB, which contains all handles for GDI objects. If you notice, there's the process ID, which indicates which process owns this specific handle. Global handles are ones that the process ID is 0. So we thought to ourselves, maybe we can teach our fuzzer to use those kinds of handles in the fuzzing process, and maybe it would find bugs. So what we did is we created a new pseudo syscall that returns handles from this list, and we let the fuzzer run for a few hours, and it found a vulnerability almost immediately. The vulnerability itself is triggered by one system call, and it's a use after free, and it involves only one global object. So our results for this part of the research were we fuzzed for about a month and a half of CPU time in our spare time. We found 8 vulnerabilities. We got assigned 6 CVE. 1 was deemed duplicate, and 1 is still pending. We found 3 denial of service bugs. one crash in WinLogon, which we are having a really hard time to reproduce, and a few deadlocks. But local privilege escalation is nice. Can we make it an RCE? So enter EMF, WMF. It's an image format that designed by Microsoft back in the 90s. It supports both vector graphics and bitmap. And if I have to summarize the entire format in one sentence, it's what would happen if we took syscalls and wrapped them up in an image format. Okay? Microsoft extended the format a few times. We have EMF, EMF Plus, and EMF Spool. And if you want to read all about this attack surface and the format, you should check out Juru's blog for more details. So we looked at the specs, and under the bitmap record types, we saw there's a stretch BLT record type. And for those of you who are familiar with GDI, there's a stretch BLT call there. And we happen to have a vulnerability in stretch BLT. So let's see a demo. So here we try to show the version of Windows. You can see it's pretty new. It was new at the time. And we're opening the EMF image. You can. We're using in front view because making it work in Word was painful. And that's it. So a bit about future work. We want to fuzz. We only touched on parts on Win32k that we were able to fuzz. We didn't touch DirectX drivers because they have input structures that are hard to model in syscaller. And we also haven't touched on Win32k callback functions. For those of you familiar, that's where a lot of bugs are. We have a huge corpus of programs for Win32k, about 450,000. So we thought that to take all of them and run them through other bug oracles, such as Boxcon, to see if they find new and interesting bugs. And finally, we want to open source our reports, and finally fuzz the rest of the kernel. But that's future work. So in summary, we started from our user space vulnerabilities, but we wanted kernel. We looked at KFL, but it wasn't good enough for us, so we moved to syscall fuzzing, and we found syscaller. We decided to port to WSL first because it seemed like the first good step. We moved to, didn't have luck, so we moved to Win32k, and we found 8 vulnerabilities, and we managed to make some of them RCEs. We want to say special thanks to the Dynamics tool team at Google, and Dimitri specifically, for creating syscaller. Dimitri will be lecturing about syscaller tomorrow, so I encourage you all to check his talk. To Omri Hershkovitzi, which assisted us in creating the presentation, and Ran Mencher for his special assistance in the research. Thank you.